Dal vivo, live. Oh,
Live?
live.
Di nuovo?
Live. Right, so... Vabbè, ma è via. Via, sì.
Dobbiamo prendere lo stesso.
Bene. Exact analysis. So the question was with everybody about there are still some region of uncertainty, and now we try to find an exact test. The exact test which tells us when the task set is feasible or not, is schedulable by the fixed period or not. Okay, so a natural question is, well, first we define this response time, Ri, of a task tau I, which is the longest time that can elapse from the activation of a task to its completion. Okay? And we define it as Ri equal to the supremo of Rij, with Rij the response time of the JJ job. So we have many jobs, each job may have its own response time, and Ri is the soup of this. What's the idea? Very simple. So we have this completion time. If the completion time is less than the deadline, then for all tasks, then the task set is schedulable. If not, it's not. I mean, there's no big things here. Okay, now how do we compute the response time? We compute it through the interference. Well, first we need to define this interference. The interference basically is the maximum amount of work which can be requested by a task with priority higher than I. Okay, so the notation here maybe is well, it's also the same here. So this is the maximum amount of work which can be requested by tasks with higher priority than I in an interval of length t. Now, using the old notation, what do we do? Well, we can write it this way. Well, the sum over all higher priority tasks of the request. This is the request, right? You remember this was the request function. So the integral between 0 and t is the cumulative request of task j in the interval. Okay. But now we are into the case of sporadic task, and this we can write in this way. We can write in this way. We have the computation time Cj and all the direct delta at multiples of the period of the task Tj. Okay. And then this we have Cj, but if you do the integral of this direct delta, you simply get this ceiling operator of t, okay? Because basically you are doing the integral of something that is like this, and you are integrating with t. And then basically, so let's say that here you have 0. Yes, something that was on a footnote, but I better do it, repeat it now. When I write integral between, let's say, any a and b of whatever, I interpret as the integral over the integral which is left closed and right open. Okay. So basically, when I do let's say the integral from 0 to 0, which is let's say t equal to 0, from 0 to 0 is the empty interval, so it's 0 because the integral of empty is 0. As I move a bit, I get immediately the first direct delta, and then I get the step. That's why, okay, the integral of this is something that is like empty here, then it goes to 1, empty here, then it goes to 2, empty here, it goes to 1. Okay? Anyway, this is a classic expression of the interference. Okay. Right, okay, here the note for myself was to make an example of interference with differentiation pattern. Okay, I do thank you for the suggestion. Let's assume that instead of let's assume that instead of a periodic task, a task with a sporadic pattern. We have a task which has an activation pattern like this, with 2 periods and 3 repeats. Let's say period long, let's see, 10, and another 5. 10, and then 5. So it's a sequence, so this task is activated this way. What interference can this task cause? So what is I, and let's say that CI, well, CI is 1, it doesn't matter, always. So here you request 1, here you request 1, here you request 1, and so on. What is I, the interference of this, or let's say this is, well, interference, okay? What is the maximum amount of interference that this task can give to a lower priority task? Well, at 0 is always 0, okay, if you know. And as the limit, the right limit is always 1. Then it stays to 1 for how long? Open question.
For 10.
For?
10.
No, I would say 5. All right, let's say that this, we have a sequence that repeats 5, 10, 5, 10, 5, 10, 5. So since you want to see the maximum, if it's 10, then it would be like this. If it's 5, then it would jump already like here. Since we want the maximum, then it's maximum when it happens at 5.
It's not real. It's not what is going on.
No. You don't know. I mean, you have to go. I mean, I of t is the maximum amount of interference that the task hypervisor can cause in any interval of length t. So I didn't write here 0. I mean,
can you have 2 activation with period 5?
Yes, I'm saying that this task is activated with a sequence of alternating separations.
So if I have 10, then I have 5. And
then 10 and then 5. Then no, it's not any.
Is it mandatory to have 10 and then 5?
Yes.
Or you can have 2 times 5?
No.
No.
I'm in this example, I'm saying 10, 5, 10, 5, 10, 5, always like this, okay? And then, so basically, the interface, the interference function here, in this case, would be like this. So we have a first jump at 5, then the next jump is at 10, 15. Then 20. Okay, so
I didn't understand. Because you why you started from the first activation? Yeah.
Because
the smaller separation
is the worst case.
Okay, let's see.
Yes.
Allora, the level is as the maximum amount of work which can be requested by tasks with priority higher in any interval of length t.
Yeah, exactly.
It's the maximum in any interval of length t. So when I take an interval of length t, if I take an interval of length 6, okay, where is it worst to put it? It is worst to put it here, because here I have 2 requests. If I put it here or here I have 0 requests. Here I have 1. Here I have 2, so it's worst, okay? And this trick is really, I mean, for example, something that is good to remember. This maximum, so for let's say for a t prime, for a t here, let's consider t a t prime. So for some value of t, the maximum may occur with an interval starting at some point. With some t prime, the maximum may occur on an interval starting somewhere else. Okay, that's also something important. Because here the interval, I mean, in this case, it's not in this case, because in this case, you place the left extreme of the interval in here, and then this is always the worst case scenario. However, there are cases when, for different values of t, the maximum interference is changed depending on the point.
So,
Yes.
so you're not considering the classical sporadic task model?
No, this is not.
Okay. Okay.
This is not.
No, I got it.
Yes, this is not the classic project. Yes, I did the example. Yes. Yes, yeah, and I contradict maybe the hypothesis that I wrote that we are using sporadic task model. Yeah, of course. This is not sporadic task model. This is a pattern of activation on its own. Okay. Okay. How do we compute the response time once we have this interference? We compute it in this way. Well, the response time of the first job of tau I is found as the smallest fixed point of the following iterative equation. So we start. So I denote Ri1 as the response time of the first job of the task I, and here I denote the index of the iteration. Did you ever see this response time before? Who did see it before? Response time analysis. Okay? So basically we start with the computational time here, and then the next iteration is nothing other than the computational time of the task plus the interference in the interval of length the previous response time. So basically, what do? Here we say, okay, this task I is activated here, and it has to execute for at least Ci. Okay? If I execute for Ci, what are these other guys with higher priority doing in the worst case? They are interfering by I of t, in this case, it's Ci. Okay, so if they're interfering, they are delaying me. Okay, so the response time with this interference is Ci plus interference. Okay, thank you. Then here, was interference here, something else, etc. etc. Okay? So now, this iteration is proved to converge if and only if utilization is less than 1. Okay? Explain its rationale basically with this drawing. Thank you for the reminder.
Actually, I have one confusion about this equation.
Yes.
It's like each step, each step, at least, for example, at step K, we compute the RIK, and in next step, we compute the interference in this RIK plus the execution time, and we get the new RIK plus 1.
Yes.
However, I'm thinking, in this way, is that we suppose that in the first step IK plus CI. In the first step IK, what if the task tau I has executed, for example, half this IK, and
yeah, but this is considered well. Okay, here. So maybe you want to subtract something here?
Yes.
Okay. The point is that if you here, you are not accounting for what you have executed. So here, this is interference. Look. Okay, let me draw it again. So you start with Ci, okay? And then we go to the first iteration. I1 of Z of 1. Okay? To compute the next one, I compute the interference not just here, but in the entire interval. So this is the interference in the entire interval. So I have, I have to put Ci inside entirely again. So it's not like this plus the interference. So I'm starting from the beginning, always, again and again. That's why I have to add the CI entirely, always, since the beginning.
I think I understand nonsense.
Okay? Sorry. Sempre ok. Va bene. Arbitrary deadline case. Okay, whatever. Right. So if the response time of the first job is less or equal than the period ti, then the first job has completed at ti. It's completed because the response time is less or equal than ti. And then the pending work at ti is 0 of the task I because it has finished. Okay? And if the pending work at ti is 0, then the max is proved that the maximum, the longest response time over time, occurs only on the first job. So basically, R1 is actually the response time of the task because it's the supremo. Otherwise, if the response time is larger than ti, we have a problem because it happens that it means that we have 0, we have ti, and we have this task which has not completed here. So the response time is we do interference, 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 and we find a value here. Okay? This is a problem. Well, a problem. It's something that, so basically, we are not guaranteed that the response time of the first job is the longest one. That's very, there is a paper where they show that actually, in the example they have, that in a condition like this, the longest response time occurs at the 5th job, so the job later on, much, much later on. So we have to compute, we have to compute the response time for the subsequent jobs. Also for R, I would use J here instead of here. Okay. So now in the of course this is something that makes sense only if the deadline is larger than the period, because if the deadline is smaller than the period and the response time here has exceeded already the period, we have violated the deadline. So we don't need to compute the response time, the maximum response time among all jobs, because we found already one job with a response time larger than the deadline. Okay, so this computation makes sense only if you have arbitrary deadline. What do we do then? Here it is here.
So you are saying that point that value 2 is on it has only sense when on the condition of value 3. Right.
It's something that can happen even if even in the other case, but we do not proceed with the process. Also, it depends on what is the goal. So if the goal is to check the schedulability, then we don't need to do that. If the goal is to compute the response time, then maybe it makes sense to compute it anyway, because maybe we say, look, we know for sure that we have violated the deadline. Okay? Let's see what is the response time. And then you need to do it anyway. Okay? So, right. What do? We compute the so-called absolute response time, which is the response time computed starting from 0. Okay, let me draw here. So say 0, ti, and 2 ti. Okay? This is what I called, let's say, R1. Let's say this guy here complete here. Okay, now I have so basically the job activated here completes here after all the interference. So this length is RI2, is the response time of the second job, while its absolute length is what I call R small I2. Okay? So the small r starts from 0. It's called like absolute job response time. So response time absolute in the sense of reference to 0. While the relative response time is the response time relative to this activation.
But it makes sense to compute the response time in this situation. So suppose that you are not scheduled, and you want to compute the response time anyway. For RBP, since you have arbitrary all that. The thing is that you have arbitrary deadlines. So my question was, okay, if you are not scheduled, probably the deadline, the response time goes to infinity.
No, not necessarily. No, it is possible that you have. Okay. I think it's like there are cases when the response time is larger than the period, but finite. It doesn't go to infinity. I don't know if I answered your question.
I think what he's asking is, do you have to check infinite number of jobs?
No, I think okay. You just say that probably the task set is not schedulable, and you are interested in computing
the response time. Okay.
Okay.
My question is, does it have sense to compute the response time since you are not schedulable? From my point of view, if I am not schedulable, the task J.
Yeah, it depends on the interpretation of a deadline. If a deadline is something that makes an airplane fall, yes, it does not make sense. Because if the airplane is falling, it's a problem. But if the deadline is something that you have just because you want to enforce some soft properties, which you may violate or not, it may sense. It may make sense anyway.
But probably for the first activation, you can find a finite response time. But for other job release, the response time goes higher and higher.
No. It's not true that it's not true that the response time goes higher and higher and higher if you violate the first job. It's not true. The response time? No.
I mean, it could, right? Because if
it could, of course it could.
Greater than 1.
If utilization is greater than 1, it could, yeah. But if it's, I mean, there are cases where utilization is less or equal than 1, which means that it's not overloaded, and the response time is larger than the period, which is fine, but still finite, okay? Okay, so what do? We compute this absolute response time in this way. So the first absolute response time is equal to the response time of the first job. No surprise. Then the next absolute response time, the absolute response time of the next job is the absolute response time plus the previous job plus 1 computation time. So we add it. And then this is just the first step for the job J. And then we keep going with this iterative machinery with the difference that now, instead of having just the computation time of one task, we compute the response time of J of one job. We compute the response time of J jobs of the task I altogether. Okay. So this is kind of the response time of a task, which has a request here of J CI. So big request of J CI. It is the absolute, and then by this way we find the absolute response time. Then in this way we make it relative, because from the absolute response time we subtract its activation. Okay, that's the math. Okay, how long do we need to continue? Well, we need to continue until until the point where it first happened that the response time, the absolute response time, is less or equal than the next activation. Okay, and if the utilization, I have a slide later. Then there are cases when this. I will explain it. But let me just show you this. Okay. Here, if I have R, I1 and T1, Ti, here it is exceeding. Let's say here it's exceeding. At some point, this completes somewhere here. Okay, here I stop. I stopped when the absolute response time is less or equal than the activation of the next job, because I have an idle. And the time from here to here is called level I busy period. This is just a term. And J star in this case is 3. So I stop up to the 3 to 3. So in this case, J star is equal to 3. Because I have to complete up to 3 jobs. Okay, so what happened? Now let's talk a bit about where it's finite, it explodes, and whatever. So when the total utilization is less than 1, strictly less, then J star is finite, because if the total utilization is less than 1, there is an idle somewhere. If there is idle somewhere, we will find it sooner or later. Okay, so this is finite. If the total utilization is larger than 1, strictly larger, then, as Fabio was saying, the limit of the response time goes to infinity because it's overloaded. Level I overload. Okay? Now, if the total is left only the case where you have equal to 1, which is quite interesting. If the total utilization is equal to 1 and the periods are linear dependent over the rational numbers, this is kind of scary. This is scary. No. Linear dependent over the rational numbers, it means that, for those of you who know the upper periods, it means a set of integers. So you have, it means that you have some h equal to ki ti for all, so it exists h for all I, no, exists h for all I, so exists h for all I, h equal to ki ti, so for exists h for all I, okay, exists ki, integer. Okay? What does it mean? It means that it exists an hyper period. It exists an hyper period, then after up to the hyper period, everything will repeat.
I have just a question on this stupid question, maybe. So if you want to check the scalability, you can verify on the hyper period. This is true for fixed priority, but also for dynamic priority. Like
Yeah, because after it repeats, everything repeats.
Okay. I was wondering, with EDF, for example, if you have variable computation times, in that case,
Variable computation time, you mean unknown?
according to probability distribution.
Okay. Job by job. So at every job,
at every job there is a different computation time.
Okay.
It's true that you have a variable scalability condition over each hyper period, or not. So, for example, I mean, there are two tasks, and at the first job, one has period 3 and one has period 5, for example. And first job, the first one.
I mean, right. So T1 equal to, okay, T1 equal to 3, and T2 equal
to 5. So at the first job, T1 takes
C1.
C1 is, for example, 2, and the other is C2 is 2 again. I'm improvising, so.
Okay. If you want to come to draw, what you have in mind.
No.
So here you have 2.
So 2.
And the second one is 2.
And the second one is 2, for example. So you.
But what is the length of the second job here of Q1 of that one?
So in that case, the second task is interrupted, right?
Yes, and here it depends on how much it takes this.
Okay, and yeah, the fact that you have variable computation times may vary the priority of the task over the hyper periods or not.
The priority, no.
The priority in the case of EDF. No, with EDF.
With EDF, the priority is given by the deadline. The deadline is given too.
Okay, because I was speaking about EDF, but I was thinking like list laxity.
No, list laxity
could be different.
List laxity is a problem because list laxity assume.
Yeah, you are absolutely right, because I was thinking about list laxity.
No, but in list laxity, the computation time is part of the scheduling algorithm. So if the computation time is a random variable,
you cannot verify a single hyper period, right?
No, you cannot even apply the scheduling algorithm. The scheduling algorithm requires to compute the laxity, and the laxity is function of the computation time of the task. If the computation time of a task is something that is unknown and it may vary, then list laxity does what? List laxity must decide something. Worst case, I don't know.
Okay, in that sense. So, okay. Yeah, that's fine. Yes, okay. Because I was confusing by the fact that the deadline is always the same. Yeah, I was thinking about like this class. Okay, it's fine.
No, okay, excellent. Okay, so right, going back to this strange case. So if the periods are linear dependent on the rational, it means that there is an hyperperiod, what is called hyperperiod. And it means that J star basically is the number of jobs that fits into one hyperperiod, okay? Right, on the other hand, if the periods are linear independent over the rational, which means that there is some irrational number, let's say square root of 2, pi, whatever. Of course, it's a kind of mathematical abstraction, right? But it's, it's nice to talk about. I'm not tomorrow implementing a task with square root of 2 as a period, but it's good to know, right? It's fun to know. But that was the point, that the J star is infinite. So the number of jobs you may need to compute is infinite. So because the schedule never repeats, and you're never finding an idle. So because of this, there is no idle, and because of this, the schedule never repeats. So J star is infinite. So you have to continue forever, but still Ri is finite. And it is the supremum of all jobs. This is a very special case, but it's fun because it's not exploding, it's not overloaded, because you have utilization equal to 1, not larger than 1. So it's not overloaded. There is no hyperperiod because there is irrational numbers, but still there is a response time. Task still has a response time, which is in this case the supremum. Okay. Okay. In human cases, this is not a human case. Okay, but it's a nice limit case to consider. In human case, then the response time is just the max of a finite of a finite set of job response time. Okay, now a bit about upper bound. Right. So doing this iteration of the response time may be time-consuming, very time-consuming because you have to do iterations, so on and so forth. So one may forget about necessity. Say, look, I don't care of this exact response time. There are cases, for example, when this response time is into an analysis tool that you have to iterate many times. Marco Di Natale is often working with this tool when you have to compute the response time. So very often the response time is the basic block of a big machine that you are iterating over and over. So if you can simplify it, it improves everything in the rest, right?
So I have a question. Which is the faster way to compute the response time? For example,
the exact response time.
Exact response time. I implemented the tool now that computes the response time by the request bound function. And then I consider all the busy periods, and then I compute the relative response time.
For arbitrary data case or
for implicit data?
Implicit data.
And sometimes it is really time consuming.
Depends on the numbers, the number of periods, on the values of the periods. I mean, if it's constrained, then it should not be, because what creates a big problems are when you have J star very big, when you have to compute many jobs ahead in the future. Okay, that takes a lot of time. So if you are in the constrained deadline case, then there is only one job. So this is already one simplification. What makes the response time computation hard is the total utilization. So as the total utilization gets close to 1, then your algorithm is going to take longer and longer. And basically that's it. I mean, the super hard conditions are these ones. Total utilization equal to 1 and periods that are linearly independent over the ratio. The closer you get to these conditions, the longer it's going to take your response time. So the closer your utilization is going to be to 1, and the closer your periods are going to be non-harmonic. So if you have very harmonic periods like 2 and 4 beautiful numbers, it's fine. If you have 13, 19, the more prime they are, the harder it's going to be.
But this is faster to compute the recursive equation of the response time, or it is faster to compute the response time?
There are going to be more iterations. The one step of the recursion is the same. The step of the recursion, the step of the recursion is, well, it's the ceiling. It's this one. It's nothing. It's constant. It's the same. It does not depend on the source of time consumption is the times that you do this recursion. It's not the time for one step. Okay? Okay. So for the above mentioned reasons, it may be appealing in some contexts to just give up with the necessities and just to find an upper bound.
You mean a sufficient upper bound?
A sufficient upper bound, okay? And how can we do that? So if we find a way to estimate the interference of high priority tasks by a linear function, so we just say, okay, look, this interference is upper bounded with some I bar, upper bound, equal to some linear function of time, okay? Then from 3, which I guess is the response time equation, what we have? We have response time less equal than the upper bound here, but this upper bound I write it this way, then I can invert and I can find that Ri is less or equal than this, which is equal to, which I defined as a response time upper bound. So if I find a way to find an upper bound of the interference, then I have with the linear, in a linear way, then I have a direct way to find the response time upper bound. Okay? Well, of course, here you have the coefficients of the linear upper bound. And then is just sufficient in this case, not anymore necessary, and faster because it's much faster to compute this than do the iteration. Then just to compute this. Okay, so now this is the last slide, I think. Yes. So what are suitable upper bounds? Suitable upper bounds can be found, for example, by replacing the ceiling with x plus 1 in the interference. Very easy, right? So if you do that, basically you find as alpha I the total utilization of the high priority task, and as beta I the sum of computation times of the high priority task. And then you plug this alpha and beta here, and you find a valid upper bound. However, we can make it a bit tighter, and there is a reference that is in the notes. But you will get the notes. When you get the notes, you see these question marks. Okay. Then you can tighten a bit. You can lower a bit beta, as you see here. As you see here, the smaller the better is the upper bound, and of course, the tighter is the upper bound. So the smaller it is this value, the tighter is this upper bound, right? And this value is a bit smaller than this because it multiplies its computation time by something that is less than 1, less or equal to 1. This is 1. And this is valid. And this is proved to be valid also in the arbitrary deterrent case. So it also avoids to compute response time at all jobs. Okay, over. Questions now and or something before what we said before. Anything?
Another stupid question.
Yeah, it's okay.
Do you remember your example of different activation patterns?
Yeah. Mm-hmm.
So you said that that task was not sporadic.
No. Sporadic in the way.
Sporadic with the minimum inter-arrival time of 5.
No, it's not, because I mean, if it's sporadic with a minimum interval of 5, then it may arrive always every 5.
It may.
While the
okay. Yeah. Your pattern was mandatory.
Yeah, my pattern was there. I assumed that was the pattern. Okay. Questions? No. Okay, we can conclude. So next one is then Monday at 10.
Monday 10.
Monday 10. Okay, thank you. Gestaci? Gestaci già all'ultimo giorno.
All'ultimo giorno.
Giorno che no.
Yeah.
Excuse me,